Good afternoon, class. Welcome to RubyConf 227, Algorithms, CLRS in Ruby. I am your, probably not professor, but lecturer at least. My name is Brad Grzesiak. You can find me on Twitter as Listrophy. A bit of my background. In 2002, I was on the 11th place team at the ACM's International Collegiate Programming Competition World Finals. Thanks to my teammates, who I rode the coattails of, but at least I have that behind me. I'm also a former aerospace engineer, so if you like to talk space stuff, grab me after. I love doing that. I'm also the founder and CEO of BendyWorks. We are a software consultancy based in Madison, Wisconsin. And I also ported the matrix library that's in the standard lib of Ruby over to mruby, actually, not Ruby. Thanks, autocorrect. That library is abandoned until mruby implements a reasonable code of conduct. So if you want to kind of push that to happen, then we can pick that library back up. Today, instead of an agenda, we have a syllabus. First, we're going to cover a little bit of complexity theory. It's not too difficult, I assure you. And then we're going to talk about three different sorts: insertion sort, quicksort, and bucket sort. We're going to then dive into dynamic programming with longest common subsequence, and then do three graph theory problems: minimum spanning tree, shortest path, and max flow. When I say that the subtitle of this talk is CLRS in Ruby, this is what I'm talking about. You can see along the left side is the author names, and it spells CLRS. It's this book. This is the second edition. There is a third edition. I encourage all of you in the class to go ahead and grab that textbook. The third edition is very different. The title is on the bottom of the cover, and the authors are on the top of the cover. But it has the same diorama thing, and it's blue. So that's the introduction. Let's dive right in. Complexity. So when we talk about complexity, we usually talk about O of something. And of course, O stands for, oh no, here comes some things. There are a number of other ways to analyze complexity. This is big O notation. There's also little o. There's big theta. There's big omega and little omega. We're not going to talk about any of that today, just big O notation. And so what this means is that if we have a collection of items and we want to do something very quickly, we might be able to do it in O of 1, so constant time. And so in Ruby, if we just address the fourth thing, we can, under the covers, one would assume that it just does some pointer math and then grabs the thing, and it doesn't have to traverse its way to the fourth thing. On the other end of the spectrum, you have O of n. And this is similar to doing a map. So you go through each of the things one after another. And so that's why it's O of n. And then somewhere in the middle is O log n. And actually, there's a function called bsearch on array in Ruby, which I'm sure not many people use. But it's there, and you can use it. And so if we had, instead of the numbers 0 to 15, but we had a sorted list of most of the letters in the alphabet, but we didn't know exactly where all of them lied, but at least they're sorted, then you could use a binary search, that's what the B stands for, to make your way through a tree to get to where you want to go. And you can see this would take 1, 2, 3, 4, 5 operations to get there out of 16 things. So the log of the binary log of 16 is approximately 4-ish, right? Or it is 4. So that's how we get the O log n. So those are our three kind of primitives that we're going to talk about. The higher up on this list, the faster the algorithm will be. And then we can actually compose things or nest things inside of each other. So for example, we could do n log n. So that's doing a log n operation inside of every time that we hit every single element. I am from the North Midwest, so UFTA is part of my vocabulary. And if you do a full run through every item while you're doing every other item, then that's O n squared. Generally, you want to avoid that, but sometimes you just have to. Like that's what the problem calls for. So that's complexity theory. So we'll go with sorting, and we've got three sorting algorithms, and the first one is insertion sort. Not something you would normally use, but we will see that it would be used in a reasonable situation later. This is the code, basically, of what it looks like. It's pretty simple. What you'll find in a lot of algorithms, which is very un-Ruby-like, is that you're often dealing with indices of things. Rather than doing like an array and mapping over it, you might do an each with index. And so here we're kind of emulating each with index by making an array or a range of indices and then doing an each over that. And so this is what it basically looks like. And let's have a quick demo. So I wrote some code in shoes. Shoes is a wonderful library originally written by Y the Lucky Stiff that basically lets you make desktop applications. So here we have a randomly sorted list of things. And so we're just going to step through this. And fun fact, I wrote a class autoloader, and I'm using fibers in this application, so that's kind of fun. So what we're going to do is we're going to make our way across the entire list. And so we're just going to sort basically one thing at a time. So when we look at 6 and 8, they're sorted already. Great, we don't have to do anything there. So we're going to move to the next thing, and we see 2 is actually less than 8. So we want to move that to the left. So we're going to kind of store 2 in this subject, and then move it left. And then see, okay, do we have to continue to moving it left? And so we do see that, so we do it again, and we're done. And then we advance to the next thing. So we have 11, that's greater than 8, so we can skip it. 7 needs to get moved to the left, you can see that, and then there it stops. And we can just keep going through there, and you can see the list is kind of getting sorted here. As we're going, the left-hand side is sorted, and the right-hand side is not sorted. So we can move the 4 down, move the 5 down about halfway. The 9 just needs a little bit, and then the 1 just kind of has to get pushed all the way. And there we have it. That's insertion sort. So insertion sort has a complexity of O of n squared. It's basically O of n squared divided by 2 because you kind of have a triangle of things. But when you're talking about complexity theory, you always just turn the constants, in this case a divide by 2, into just 1, and you don't even worry about that. So insertion sort is O of n squared. Next, we have Quicksort. This is kind of the go-to mechanism for sorting things. And it looks a little bit like this. It is actually a divide and conquer algorithm. And the way that it works is that you partition your array into 2 sets, and then you recursively sort each of those partitions. So we have the top-level quicksort that basically calls this helper. The helper bails out if it's in a too small of a state. It does the partition, and then it recursively Q-sort helps each of the 2 partitions. So you can see the first iteration, the P is going to be 0, R is going to be at the very end, and then we're going to sort each of the partitions. And then you can see the partition code on the right. It has some swaps in it and stuff. Kind of complicated, but again, I have a demo. So let's take a look at that. And of course, it shows up on the wrong screen. OK, so we have the same shuffled array. And what we're going to do, this is basically how Quicksort works. We're going to pick what we call a pivot. And in our case, we're just going to pick the last element of the array as a convenience for the underlying implementation. So we're going to pick the very last thing, and that's a 7. And generally, we want to find a pivot that's about halfway in the middle. And we're lucky in this case because 7 is somewhere in the middle. At least it's not an extreme value of 1 or 11. And on the left, you can see kind of a purplish line off on the edge. And that is the point at which we're going to decide that everything to the left of that line is going to be less than the pivot, and everything to the right of the line is going to be greater than the pivot. And you'll see why that matters once we make it through through the whole list the first time around. And the bottom black thick bar indicates the elements that we're considering on this pass, right? So the first step, we're going to consider the 8. 8 is greater than 7, so we're not going to do anything because it's already to the right of the line. 9, same deal. It's greater than 7, so we're going to keep it to the right of the partition line. 2 is different. 2 is less than 7. So what we're actually going to do is we're going to swap 2 with 8, and then we're going to move the partition line to the right by 1. So we'll see that here. We swap them, and then we move the partition. And so here we have this invariant where to the left of the line are things that are less than 7, and to the right of the line are things that are greater than 7. We haven't made it to the end of the list, so not everything is moved over yet. So we keep moving forward. 6 is less than 7. We're going to make that swap again and move the line. So because 6 is less than 7, so it needs to be on the left of that partition line. So we keep going through the list, making these swaps and moving the line. 4 needs to be swapped. 11 does not. 1 definitely does. And then 5 does. And so we get to the end here. And the last thing that we do is we actually make a swap of 7 with the 9. And once we do this, we know that 7 is actually in its final position, which is kind of cool. So now we have to recursively implement this algorithm for all the elements left of 7, as well as all the elements to the right of 7. And so you can see the bar is shifted to the left, and so we're only going to sort these. So we kind of got stuck with 5. It's not a great number to get stuck with in this situation, but we'll make it through the steps. So 2 is less than 5, so that it gets swapped with itself, basically, which is a weird edge case in the algorithm. But the code works, and we shift that partition line. And then we make our way through. Swap the 3, move the line. Swap the 4, move the line. Swap the 1, move the line. And then put 5 where it needs to be. And then 6 is actually going to be in its own spot, too. We don't know that yet because we haven't recursively done anything there yet. So we can continue moving forward, swap the 1, and then this is kind of like not a great situation to be in, but it eventually works. So we popped out of that recursive thing, and now we're going to do the right side. The 6 was already done, and now we can do the right side. So comparing everything with 9, the 8 is less than 9, so we're going to swap that with the 11 and move the line, do that swap, and we're done. And that's how Quicksort works. Now Quicksort, because it's a divide and conquer strategy, it basically implements that binary search kind of idea of log n. So we actually get to have an O of n log n runtime, which is pretty great. Now, a couple of days ago, I posted on Twitter a poll of like, if you know the general distribution of your data, what is the expected runtime that you can achieve for sort? And most people said n log n. And most people are wrong. This isn't to shame anyone who said O of n log n, but it's a pointer to step back whenever you're asked a question and say, well, the common knowledge is O of n log n. Like, people say that that's the proof. But I added a condition here where if you know the general distribution of your data, which changes the context of the normal question of what is the best sorting algorithm, and the answer is, well, it's going to be O of n log n. But if we know the general distribution, we can actually achieve O of n. And there are a number of ways to do that, but one of them is called bucket sort. Bucket sort basically generates B, which is kind of the destination list. And then you go through each of your items and then place them based on their value into the bucket where they belong. And at the very end, we see our old friend insertion sort, because usually if you have your bucket allocation algorithm written in a good way, usually you'll only have one to 3, maybe 4 items in each bucket. And so for something that small, you don't need something as powerful as Quicksort. Actually, the spin up and spin down time of Quicksort is actually detrimental, and you can just get away with insertion sort in this case. And then once we have all our buckets of buckets, we flatten and compact them, and there we have it. There's a special case of bucket sort even that's even better than this. If you know exactly what the distribution and type of data that you have, you can actually do a little bit better and have it as simple as this. In this case, you might think of, I have a deck of shuffled cards, and let's say clubs are the lowest and hearts are the highest, or what have you. And you have a customized table that has a slot for each of the things, each of the cards. And so you can actually go through each card, evaluate the address of where it would be on the table. So, oh, this is a 42, so I'm going to put it in the 42nd slot based on its suit and its rank. And you can just make your way all the way through and have like a legitimately O of n sorting algorithm. So let's take a look at that. We're going to look at this case where it is kind of like that deck of cards situation where you know exactly you have the right number of things and the right number of slots. So move this thing over again. So we have our things. We have our destination array that's empty right now. And so we're just going to make our way through the list on top. 7, boom, goes to 7. 5 goes to 5. 1 goes to 1. And you can see that this is just going to get to the end and be done, and everything's going to be sorted. So when you're faced with a situation where you know something a bit about your data, you can get away from the standard idea of how sort works and kind of use a trick to get around it. So that's it for shoes. Thank you, shoes, for not crashing on me. If you're interested in making toy applications, I highly recommend shoes. It's a lot of fun. There's a bit of a learning curve, but it is all in Ruby. So, bucket sort complexity is O of n, kind of. If you apply bucket sort to a collection of things where you don't know about the distribution and you inaccurately implement where the buckets go, you could end up with all your items in one bucket and then run insertion sort on it, and you're in O of n squared situation. So that's not great. But if you know how to appropriately put things into buckets, it's a great algorithm. All right, let's move on to dynamic programming. Now, dynamic programming sounds like a huge buzzword, but it actually has a very technical definition. And while we talked about just now divide and conquer strategies with Quicksort, divide and conquer, it's always addressing independent problems. Whereas in dynamic programming, there's a dependence between a previous calculation. So you can think of it as like, I'm going to cache the result. A typical implementation might be a good Fibonacci implementation where you're caching the result instead of recursively all the way going back to 1 on every single thing. So that would be a dynamic programming implementation of Fib. So we're going to talk about longest common subsequence. Does anyone know what this algorithm does? We've got like 5 hands that are half raised. So the classic example that we use when we talk about longest common subsequence is matching genes together. I have no idea why, but this seems to be the go-to problem. So we can see we have 2 strands, and we want to find what we call the longest common subsequence is between them. And I'm going to show you an animation that kind of shows in motion what that actually means, instead of trying to explain it in words. So all right, watch this. So they're going to spread apart, and we're going to match up the pieces that match. So the answer here is basically 6, a length of 6, and the longest common subsequence is ACCGTC in this particular case. Fascinating, right? Really applicable to our everyday life. Something that's a little more applicable is getDiff. In this case, every line that's white is the longest common subsequence of the two sides of the commit. Thank you, Coraline, for the source material. And we see that on the left we are refactoring the setting of subject, and on the right we're adding a cache optimization, and then below we're implementing that refactoring. There's actually an extra line of things that was added to that subject calculation, and that's why it went from a single line, and the addition of that one thing made it a little too long, so put it on a couple of lines. And so here we have the white lines, which are the longest common subsequence. So to calculate the longest common subsequence, we're going to take the example of A through F along with B, D, F. And the answer to this is really easy. B, D, F. 3, right? Each of the letters B, D, and F appear in that order in A, B, C, D, E, F. But we're going to use this example to illustrate how the algorithm works. So we set up a 2x2 array, as you can see. And basically for each item, and we're going to start in the upper left, go across, and then just start again, one line down. And if the two things that we're comparing match, then we're just going to take whatever is to the up and left of this and add 1. And otherwise, we're just going to take the maximum of what's above us and what's to the left of us. So we'll see it here. So first of all, and assume that all out of bounds values are 0. So we're going to start. A and B do not equal each other, so that's a 0. Here we have our first match. So B is equal to B. So what we're going to do is take the value up and to the left, which is by default 0. We're going to add 1 to it, so we have a 1. Now we go to the next one, and C, it does not equal B, but the max of the 0 above and the 1 to the left is 1. So we keep propagating that through. And then we just start again at the very bottom. And this is the point where we do better than divide and conquer, because we're going to be using the calculations that we had before and not recalculating what the value was above. So here A and D are not equal, so that's a 0. And here we're going to take that max of 0 and 1, which is 1. So we're going to make our way to the point where D equals D, and we're going to take the one that's to the up and to the left, where C and B intersect, and add 1 to that. And we just make our way through. Keep doing the same thing, and you end up with this kind of nested rectangles in your answers. And the last answer that we get is a 3, because the 3 is 1 plus the 1 up and to the left, because F equals to F. And that's longest common subsequence. Longest common subsequence, if you were to naively implement this probably would be like a O of n cubed. But if you're doing it like this, you can actually get by with O of n times m, where n is the length of one of the things and m is the length of the other thing that you're comparing. So it's a pretty quick algorithm. And if you're ever going to write your own get diff algorithm, this is probably something that you'll want to look into. This is kind of what it looks like. We're going to set everything up. We're going to compute that matrix and then grab the last thing. Just make a bunch of arrays. And then we're going to iterate through each of the things. We're going to compute that cell. If it matches, then do one thing. If it doesn't match, do the other thing. Add 1 to the up and to the left. Otherwise, just take the max. And that's working Ruby code to implement longest common subsequence. Graphs. This is my favorite part. This took a lot of effort to put these slides together, so I hope you appreciate it. The first algorithm that we're going to talk about is MinimumSpanning Tree. So let's start off with an example of a graph. A graph is nodes and edges. Sometimes they are directed, where the edges have a direction to them. Other times they are not directed, or undirected. And in this case, we have an undirected graph. We have nodes A through I, and we have some weights associated with those edges. We're going to apply an algorithm called Prim's algorithm. And this is all it is, basically. You do have to implement what's called a priority queue. And if you want to have the most performance, you'd implement it as a Fibonacci heap. And yeah, whatever. We're not going to talk about that part. But we're going to talk about this algorithm. So until the priority queue is empty, we're going to extract the topmost thing. And then we're going to see if the queue has the thing that we're attached to of each of its neighbors, and the weight of that is lower, then we're going to just update that other node. So let's go through that one by one. So we're going to start with A. We're going to pick A because we want to. And A's neighbors are H and B. And so we're going to go to H, and we're going to go to B, and basically highlight those edges and update H and B. Next, we're going to go to B, and we're going to look. Well, we're not going to update H, because if we added that 11 edge, that would be worse than the 8 that's already connected. So we're not going to add that, and we are going to add the C node, because the C node is not part of the tree yet. Next, we're going to go to H, because that was inserted earlier. We're not going to add the line down to B, again, because B is already connected, and B is already connected at a value of 4, so we don't want to add the 11. But we are going to add G and I, because they're not part of the tree yet. Moving forward, we're going to do G. G is only connected to F, so we'll add that. F. F, we have 3 things to consider. E and D are easy, because they're not in the tree yet, so we're just going to add them, right? But then we consider C. C has a value, was added in an operation that had a value of 8. And now we have an opportunity to add it to the tree with a value of 4. So we're actually going to turn off the 8 and add the 4. And then we're going to also add E and D with values of 10 and 14. And we're going to continue. For C, we're not going to add B, because that's already added with a 4. We're not going to add F, because that's already added with a 2. But D is going to change, and it looks like I is going to change as well, because I was added with a 7. And we can do better than that. We can add it with a 2. So we see the tree is morphing as we're going. Next, we're going to look at I. That's a no-op. Nothing needs to change there. D, also nothing going to happen. Or we're going to add E, because E was added with a 10. And now it's going to be added with a 9. And then E is the last one. We don't have to do anything. And that's Prim's algorithm. And this minimum spanning tree is the set of edges that connect all the nodes in the lowest possible cost. And the complexity on this is a little strange to interpret, but it's E plus V log V, and that's all I'm going to say about that. Next, we're going to talk about shortest path. So this is getting from the left, in our case, we're going to say get from the left side to the right side in the lowest amount of cost. So again, we have the exact same graph, and we want to get from A to E. And so the first thing, so we're going to implement a relax method. I'm from Wisconsin, and that's like Aaron Rodgers, like famous, like RELAX, relax. So we're going to implement that on each node, and then we're just going to iterate through all the nodes and run relax as we're adding things. So we're going to start with A, and that has a cost of 0, because that's where we're starting. Okay, so the next thing we're going to do is we're going to add H and B, and we're going to update H and B to have a new cost based on how costly it was to get there, right? So those are going to be 8 and 4, pretty easy. Next, we're going to consider B, because that has the lowest value currently that we haven't already processed. And once we consider B, we look at H, of course. But if we added H through that line of 11, that would result in a higher cost to get to H through B than it would be just to get from A to B. So we're not going to add that, but we're going to add C because it's not in the tree yet. So we're going to add that. And notice that C now has a 12 because that is the addition of the costs to get from A to C. Next, we're going to consider H. H, of course, is not going to add B because you can get to B in 4, and 8 plus 11 would not be a great way to do things. But we are going to add I and G. And so I gets 15 because that's 7 plus 8, and G gets 1 more than H because it costs just 1 to get there. Next, we'll go to G. That's pretty simple. There's only one way to go. So we'll get 11 all the way to F. Next, we'll consider F because that is the currently outstanding, we haven't processed it yet, lowest cost node that we've gotten to. And when we consider F, we're going to add E and D. But this time, if you remember last time, we added C when we did this. This time, we're actually not. Because if you take F's value, or cost, of 11, and add the route of 4 to it, then you get 15, which is already higher than what it costs to get to C already. So we're not going to add it, but we are going to add E and D. Now, you might think we're done. We've made it to E. But if we keep going through the process, we will actually make that 21 a bit smaller. So the next thing we're going to do is consider C. And this is the first time where we're actually going to change the weight of getting to a node. We're going to look at I. And if we're at C with 12 and we try to get to I with an additional 2, we'll have 14, which is less than what it currently costs to get to I. So we're going to nix out that 7, add the edge of 2, and relax the value of I. And we're going to do the same thing with D. D is currently at a cost to get to of 25. But we're at C of 12, and if we add 7, we can get to D in 19 instead. So we'll do that. Next up, we'll consider I. Nothing happens with I. D, we'll consider getting to E. And actually, I missed a step here. No, I didn't. If we wanted to go from D to E, that would be a 19 plus a 9, which is not actually what we would do. And so, the final answer to get to E is actually 21. So that's what it costs to get to 21 in the minimum cost, the shortest path. And the complexity of this is the same, actually. If you use that Fibonacci heap for the priority queue, it'll be E plus V log n. All right, last algorithm, max flow. For max flow, we're going to use what's called the Ford-Fulkerson algorithm, which looks like this. We're just going to find a path from the start to the end. And we're going to change up the graph a little bit because in this case, we're supposed to use directed edges instead of undirected. So we're going to have arrows at the end of our lines here. So we're going to just find a path. And we're actually going to use breadth first search to find that. Next, we're going to, for each of those segments in that path, from the source to the sink, so we always called the sink T for some reason. For each of those segments, we're going to take the smallest capacity, or the smallest remaining capacity of that line. And we're going to store that as the residual capacity of the path P. And then we're just going to augment the path with that amount. So if we have huge pipe, little pipe, and the little pipe can carry 3 more, then we'll just add 3 to the whole system, and then keep doing that until we can't add it anymore. So here's our new graph. We have arrows. We have an S, the source. T is the sink. I suppose you can't really have 2 S's, so that's why they call it T. And we want to find how much stuff can we put through these arrows to get to T? What is the maximum flow? So we're going to find our first path from S to T, and we're just going to pick this one on the bottom. S goes to C, C goes to D, D goes to T. And you can see intuitively that the smallest capacity remaining is 4 on that last piece. So we're going to propagate that 4 across all the remaining things. Because if we put 13 into this path, it would get bottlenecked on that last path, or that last segment of the path. OK, we found one. Let's find another pathway to get from S to T. And we find one up here on top, 16, 12, and 20. And of course, the minimum here is 12. So we add 12 to that path on each segment. And what we're left with is one more path to get to T. And that's through this circuitous route that goes C to D and then up to B and then over to T. And here we can't just automatically pick 7. The answer will be 7. But we can't just pick 7. We actually have to go, because that first pipe, that 13 that has a 4 on it currently, it doesn't have a capacity of 13 anymore. It has a capacity of 9, right? Because 4 of it is already being used. So that segment has a 9. The next segment, 14 minus 4, has 10 remaining. The 7 has 7 remaining. and the 20 has 8 remaining. So the answer does happen to be 7, but it could have been something else. So we add 7 to that segment and propagate that out and increase all of them. And that's what we get. We now have the maximum flow in this network from S to T. We actually don't use the back and forth arrows over on the left, and then we don't use the 9 that's coming back. Now, an interesting corollary to the max flow is the min cut. So if we were to take a knife and slice through this graph in all the possible ways that you could do that, if you find the cut that cuts the least amount, that is the area where that is the bottleneck, effectively, of the entire system. And so we can see that here. That cut is saturating all of the arrows that are going from the left side of the graph to the right side of the graph. We're not saturating the 9 that's going left, but that's going in the opposite direction of the overall flow, so we don't consider that. But we can see here that that is the cut that has the minimum weight, and that is therefore the maximum flow. It's the bottleneck point. And to make complexity stuff for this a little bit trickier, the complexity is the number of edges times the maximum flow, which stinks because you don't know the maximum flow until you've finished. So you could potentially construct some very unfortunate situations where this algorithm just churns and churns and churns and churns, eventually gets to the right answer, but it could be very costly to get there. Anyway, that's the algorithms that I wanted to cover: complexity, insertion sort, quicksort, and bucket sort, dynamic programming with longest common subsequence, and then 3 graph algorithms: minimum spanning tree, shortest path, and max flow. I have the code for the Shoes app and implementations of each of the other topics that I shared on gitlab.com/listrophy/CLRS algorithms. I think it's important to state that there's a conscious reason to go with GitLab, even though it's open source. It allows me an opportunity to talk about why, which is their contract with ICE. You might not agree with that, but that's what I want to do with my time up here. And you can follow me on Twitter as Listrophy, and my company BendyWorks. We are hiring. And next time I put a post with a poll on Twitter, I would love to see a few more votes from everyone. Thank you so much for your time.